All right, hello and welcome to what, knock on wood, will be our last live stream of the semester. Um, again, YouTube will continue to be here. I have a bank of lectures recorded in the fall semester of 2020 that you're more than welcome to use to help study, prepare for class, etc. Hey, Jessica, how's it going? Um, but Randall, good to see you. Um, it's going to be a challenge because I'm starting to learn some names, um, but I'm also associating them with the little what do you call it, profile picture thing in YouTube. Raisha, good to see you. But yeah, knock on wood, we should be back in class for the first time in 2 years on Monday. So unless I hear otherwise, I'll see you in person, which will be awesome. Kendall, good to see you. Um, if I do hear otherwise, I will post an announcement to Canvas. But hopefully things should be good. Um, it's a good Wednesday. In case you're wondering, I am drinking out of the best coffee mug in existence. You can't see it because it's one of those ones that like it's dark and then it opens up when it gets warm. You can see I'm this much done with my cup of coffee, but I have Nicolas Cage's beautiful mug on my mug. You can kind of see it there. But now you won't be wondering as I move through lecture and take a sip what the heck that is. You now know. Oh man, Madeline, Mason, Morisan, Nee, Nargis. Oh, and Nargis. Hello and welcome, one and all. I'm optimistic. I'm really optimistic about getting back into the classroom. I have definitely missed it. Song of the day, you can hit it up in the description, is Garbage Man by the Cramps. Willow, good morning / afternoon. We kind of crossed that transition in the middle of the lecture. Garbage Man by the Cramps. David, hello. It is my 3-year-old. We have a thing before nap time, before bedtime. He gets to pick out a song, and for the past week solid, it's been nothing but the Cramps. So if you're unfamiliar with them, they're kind of pioneers of horror punk genre, alongside the Misfits. Seif, great to see you. But they're a little less well known. They're not as well known as the Misfits, but possibly more influential. Definitely influenced a lot of punk bands, but also the noise rock genre, if that's something you're familiar with. They're also, fun fact, from Sacramento originally. They met at the lead singer and guitarist met at Sacramento City College. Of course, they moved to New York, and that's where their career launched, as you do if you're trying to get into punk. But there's Bay Area punk. Oh, well, anyways, let's start talking about chemistry. How about that? We left off with Lexi. Hello and good morning / soon to be afternoon. Excuse me. So we left off with an example problem, one that I said was kind of next level. So let's go ahead and dive in and see how this thing shakes out. If you've done it, you're about to see if you got what it takes. Zoe, good to see you. Zoe, you share a last name with my tattoo artist. If any of you are looking to get tattoos and you happen to be in New York City, go get tattoos from Jonah Ellis. He works at Inside Ink. And he's the man. Whoa. HA. How about HO? How many molecules of water? Annabelle. Hello. Are contained in 1.000 milliliters. And we're told that the density, H2O, of H2O, density of water, is 1.008 grams per milliliter. All right. Now, what we have on our hands. We've never done a problem like this before. And that makes this a simulation of an experience you will feel when you take the exam, and any exam. There will be a mix. There will be problems that you've seen. There will be problems that are similar to homework problems, but then there will be problems that you've never done before, you've never seen before. Because on the exam, I'm not testing your ability to memorize. That's what we have computers for. I'm testing your ability to think and problem solve. So, this is a simulation of that. We've never done a problem like this before. Let's see how we break it down and get to an answer even though we don't know exactly what we're doing. Step number 1, you always identify what you are trying to find. All right, and that is right here. Oh, sorry. This should say how many. I just realized I wrote how molecules of water. How many molecules of water. So we want to find molecules of H2O. Let's look at what we're given. First piece of given information is we're given a volume. Oops. We're told that we have a volume of 1.000 milliliters. All right. Second piece of given information is the density. We're told that the density of water is 1.008 grams per milliliter. Now, that is all the explicit information we've been given, but we have actually been given more. So density is a quantity that has an algebraic expression. There is an algebraic expression for density. Every time you're given a quantity, so here we're told density is 1.008 grams per milliliter. Whenever you're given a quantity that has a corresponding algebraic expression, it is worth your while to write out that algebraic expression under your given information. You don't need to memorize these. I provide a cover sheet for the exam, which has the periodic table and any algebraic expressions you need. So you don't have to memorize them. And they won't be listed with the explicit problem. So I would give you a problem like this. Density would be on the cover of your exam. So it is given, it's just not explicitly here. You want to write that down under your given information because here's the deal. This algebraic expression, these algebraic equations will often provide you a roadmap that you can use to solve the problem. All right, and what do we mean? Well, if you look at this expression, density is equal to mass times volume, you'll notice that we have been given both density and volume. So what does this expression do? It lets you solve for mass. All right, we will be able to find grams of water using this expression. Is that what the problem is asking for? Not exactly. We can find grams. We're being asked to find molecules of water. And this is where light should be going off. Because we introduced the concept of moles at the end of lecture last week. And moles is a bridge between atoms and grams. It's also a bridge between molecules and grams. Because remember, 1 mole is 6.022 times 10 to the 23rd things. So you could have a mole of atoms, you could have a mole of molecules. So we can go from grams to moles of water. And then we can go from moles to molecules. So this is the roadmap we want to follow. First, we're going to use the equation for density to find our mass of water. Then we can convert our grams of water into moles and our moles of water into molecules. So that is the roadmap. Let's start doing the heavy lifting. So first, we have density is equal to mass over volume. We want to isolate mass on one side of this equation, so we're going to multiply both sides by volume, which is in the denominator, which gives us the expression, mass is equal to density times volume. All right, now we know our density is 1.008 grams per milliliter, and our volume is 1.000 milliliters. When you multiply these together, your calculator will tell you that 1.008 times 1.000 is indeed 1.008. Couple things. First, you'll notice that milliliters cancel, so the only unit left is grams. Next, when you look at sig figs, our density has 4 significant digits, our volume has 4 significant digits, so our answer must have 4 significant digits, and it does. So sig figs wise, we're fine. That is our mass. Now, that's part one. Now we need to take our mass and convert it to moles. So we have 1.008 grams of H2O, and we want a unit conversion that will cancel our grams of water and leave us with moles. Now, we've done conversions between grams and moles before, but this is where this problem stretches us one step beyond of what we've seen before. Because before, when we were closing out lecture on Monday, we were converting between like grams of copper to moles of copper or moles of carbon to grams of carbon. You'll notice water is not an element. You will not find H2O anywhere on the periodic table. You will, however, find hydrogen. Hydrogen has an atomic mass of 1.008, and oxygen has an atomic mass of 16.00. So what we can do is we can add up the atomic masses of all the elements in our molecule, and that will give us the molecular weight. The nice thing about doing grams to moles for an atom is you just look it up on the periodic table. For every molecule, you have to add up the atomic masses of each individual element in your molecule, and that will give you your unit conversion. One thing to be aware of is there are 2 hydrogens in our molecule of water, so we actually need to multiply the atomic mass of hydrogen by 2 to represent both hydrogen atoms that are in our molecule of water. Once you do this, it comes out to be 18.016 sig figs wise, based on the numbers that I'm using. If you're using a different periodic table with a different precision, this may come out differently, but based on these atomic masses, our last sig fig needs to be in the second decimal place. Again, I'm not rounding right now because I'm not rounding because we round at the end of the problem, but I am going to put a line under the second decimal place to remind myself that this number has 1, 2, 3, 4 sig figs. All right. So we have set up our first unit conversion. Grams of water cancels grams of water. Next, we want to convert from moles to molecules, and to do that, we need to use Avogadro's number. We want moles of water to cancel. We want to find molecules. One mole has 6.022 times 10 to the 23rd molecules in it. So moles of water cancel, and now we're ready to crunch our numbers. Let's see, where's our okay. So let's say we have 1.008 divided by 18.016 times 6.022 times 10 to the 23rd. My calculator is telling me that my answer is 3.369325044. Times 10 to the 22nd. All right, sig figs wise. 18, my molecular mass has 4 sig figs. Oops. My mass has 4 sig figs, and Avogadro's number has 4 sig figs. So it's a 4-way tie. We're keeping 4 sig figs. This 3 rounds down. So our final answer will be 3.369 times 10 to the 23rd. That is the correct value with the correct sig figs, but we also need the correct units. This is molecules of water. All right, and that is the answer. So hopefully you took a crack at this on your own. Hopefully that is the solution you came up with, and that's how you do that business. All right, so this actually brings to a conclusion chapter 2, and we are going to now venture in to chapter 3. Yes, it was 10 to the 22. What did I put? Oops, not that one. Oh, Mason, you're totally right. Yes. Good catch. Oh, hang on. There we go. Times 10 to the 22nd. Yeah. No, not 10 to the 23rd. It is 10 to the 22nd. I was right this time, and I made a transcription error there. So, what would happen to me on an exam? Well, I got the correct sig figs and the correct units right, but if I wrote 10 to the 23rd, I would have the incorrect value, so I would lose points there. Granted, because I showed all my work, I would score the majority of the points on this problem, but I would get dinged right there at the end for not sticking the landing on 100%. Great catch, everyone, Mason, Randall, and Raisha. Nick Cage still smiles on you for a little while longer. All right. So this brings to brings to a conclusion chapter 2. We're moving into chapter 3, and chapter 2 is a bit of a molecule parade. But chapter 3, we get to begin a discussion of molecules. We're going to start looking at molecular structure, etc. And we're going to begin with kind of like a scheme of organization. So we're going to look at, of all substances, we're going to begin with an investigation of pure substances, so you can break all pure substances down into 2 categories. Pure substances can be broken down into, there are elements and there are compounds. All right, so all pure substances can be categorized as either elements or compounds. Elements, all atoms in an element are the same. Compounds are pure substances comprised of different atoms. And now that might seem like a contradiction in terms. What do you mean? How can it be a pure substance if there's different atoms? We'll get there in 1 second. First, we're going to look at elements. Elements can be broken down into further into two categories. There are atomic elements, and there are molecular elements. So, examples of atomic elements would be copper. All right, if you have a sample of copper, it's just literally a bunch of copper atoms just smushed, lined up together. That's what copper wire is. Gold would be another example. If you have a pure gold ring, it is just a bunch of gold atoms, again, smushed together. Molecular elements are, for example, hydrogen is a molecular element because there's only hydrogen atoms present, but one hydrogen atom bonds to another hydrogen atom to make what we call molecular hydrogen. Oxygen is the same, as is, actually, sorry, I messed up that order. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all examples of molecular elements. They're elements because all the atoms are the same, but they're molecules. It's two of the same element bonded together. These are called diatomics, homonuclear diatomics. They're not the only type of molecular element out there, but they are an important type of molecular element, and I wanted to highlight this for you. Mostly because, again, it's my philosophy to try to keep memorization to an absolute bare minimum. This is one of those things that you just need to know. You do need to memorize these dudes. You need to know when you're reading a problem that it says hydrogen is produced, that it's not producing H atoms, it's producing H2. And the reason why I'm bringing this up here is because you can memorize them, which I recommend doing. But you can also use the periodic table to help you out. So notice how I made this kind of dog leg: nitrogen, oxygen, fluorine, chlorine, bromine, iodine. That's because the homonuclear diatomics are kind of located right here in this dog leg on the periodic table. You'll notice they're all here except for hydrogen, which is just hanging out here. But if you remember, it's this corner. Start with nitrogen, Noph, and then Culbury. If you go down that way, those are where your homonuclear diatomics are. So if you just remember that, you don't have to memorize the individuals. But don't forget hydrogen. You need those in your head because it won't always be explicitly stated in the lab, in the textbook as you're doing problems. It's important to be aware of these guys. All right, so those are elements. What about compounds? How can compounds be further divided into categories of pure substances? There's two compounds come in two flavors. There are covalent. Covalent compounds, and there are ionic compounds. Ionic compounds are made of ions, which we'll talk about in a bit. Covalent compounds are non-ionic, which what ionic means, what an ion is it has a charge, positive or negative charge. And non-ionic compounds involve no charges. All right. An example of a covalent compound is H2O is a covalent compound. An example of an ionic compound would be salt, sodium chloride. And the reason why these can be pure substances, even though they're comprised of different atoms, is a water molecule, for example, will always be an oxygen atom in the middle with two hydrogens bonded to it. And that configuration repeats itself. So it'll always be, there's one molecule of water, here's another molecule of water, and it just repeats over and over and over. And you can have a pure sample of this repeating H2O unit. Likewise with sodium chloride, even though they're different atoms, they're repeating it. Sodium chloride, NaCl, followed by NaCl, followed by NaCl, and stacks together to make a pure substance, even though there are different atoms involved in the actual molecule. Hopefully that makes sense. All right. Now, we are going to focus our attention for now on ionic and covalent compounds. We're going to be naming them. We're starting our discussion with ionic, and then we'll transition to covalence. I want to give a warning up front. So we're about to start a section on nomenclature. Which is a fancy word that simply means naming. So we're going to start by learning how to name ionic compounds, and then we are going to learn how to name covalent compounds. But I wanted to give a warning. Issue a caveat emptor, which is Latin for buyers beware. If you have not started yet, and I don't know what the specific due dates are because these are set by your lab instructor, but as you know, looking at the lab manual, there's lab reports and then there's lab exercises. And the lab exercises, I don't know if you've cracked it open to take a look yet, but it's basically just these extended worksheets. And lab exercise 2, specifically, I recommend starting this ASAP. Lab exercise 2 is basically just a worksheet that's filled with compounds. You'll be given names, and then there's a blank space where you have to write in the formula. There will be formulas and a blank space where you're going to be asked to write in names, and it's a mix. There's naming ionic compounds, naming covalent compounds, and then switches them, and acids as well. We'll talk about it all. But the reason why I recommend starting this as early as possible is because there are over 200 questions. And again, it's not like the individual questions take that long. It's like literally, here's this molecule, name it, or here's this name, draw the formula. But if you wait to start this the night before, I've had this happen with students where they come into lab and they're like all like, their eyes are all like bloodshot and they look totally thrashed and they didn't finish it. If you start this thing last minute, that could happen to you. So I'd start this as early as possible. Again, today we're going to start talking about naming ionic compounds, and we probably won't even finish that discussion today. But what you should do after this lecture is over is crack open your lab exercise 2 and start doing the problems you know how to do. If you see a compound that you don't know exactly how to name, don't stress. We haven't covered it yet. By the time we're done with chapter 3, we'll have covered all of that situation, but do the ones that you know how to do, the ones that you recognize, and then come back and you can kind of work it as we move through it in lecture. All right. I'm done with advertising. I'm done with my caveat emptor. I'm just trying to save you stress. Hopefully you take me up on that and work on this progressively. All right. So let's talk about ionic compounds. All right. Ionic compounds are comprised of an anion, and a cation. All ionic compounds are net neutral. Which is another way of saying i.e. the total positive charge equals the total negative charge. All right. Now, a anion is a negative ion, and a cation is a positive ion. All right, so every ionic compound is comprised of, there's an anion present and a cation present. If you like cats, this is easy to remember because you're like, oh, cations are positive. If you're a dog person, I don't know what to tell you. You're out of luck with this analogy. But cations are positive, anions are negative, and all ionic compounds are net neutral, which means that your total positive charge and your total negative charge have to equal each other. They have to cancel each other out. There's going to be no excess charge in an ionic compound. Now, the way you name ionic compounds is fairly straightforward. The name of any ionic compound is, you write the cation name, space, and then you write the anion name. All right? That's all there is to it. Now, so for example, if I were to ask you to name this ionic compound, NaCl. The cation always comes first. Cation name always comes first. And this cation is sodium. So our cation name here is sodium. All right, we're halfway to naming this compound. Our second element here, this is chlorine. All right. But something that you should be aware of. Chlorine is the name of the atom, but the anion name is not chlorine. For cations, your atom name will be the same as your cation name. But for anions, you have to take your atom name, chop off the end, and add IDE. So the anion name for chlorine is chloride. All right. So when you name an ionic compound, name the cation name is the same as the atom name. So sodium chloride. You have to change that ending to an IDE. Randall, that is 100% correct. Sodium chloride. So you take that atom name, chop off the end, add IDE. All right. Let's do a few more examples. Let's name MgBr2. So we're going to start by looking at our atom name here. This is magnesium. Is the name of that first atom. The name of the second atom is bromine. So if we're going to name this ionic compound, our cation name is magnesium. Our anion name is based on our atom name, bromine, but we have to chop off the end and add an "ide." So this would be magnesium bromide, would be the name of this ionic compound. Yeah, Alexander, 100%. You always add "ide" for the anion. Let's do another example. Let's do Al2O3. All right, here our cation name is aluminum, because that's the element aluminum, and the cation name, you leave it alone. Our atom's name for the second one is oxygen. All right, but again, we got to chop off the end and add IDE. So this is aluminum oxide. All right, one of the things I want to point out here, you look at aluminum oxide, it was Al2O3. Magnesium bromide was MgBr2. Sodium chloride was NaCl. You'll notice that when the reason why I started naming ionic compounds before covalent compounds is it's, in a sense, it's simpler. It doesn't matter if there's 2, 3, 1. It doesn't matter the quantity of the ions present at all. It's just always cation name, anion name. All right? So it's straightforward. You don't have to keep track of how many of each there is. It's always cation name, anion name. All right. Now, let's go ahead and look at, so we've done some examples taking the chemical formula and writing the name. Let's do some problems where we work in reverse. For example, let's write the chemical formula for potassium fluoride. Now, this is a little bit more challenging. One of the things you'll notice about the examples we did before, where we had the formula and wrote the name, is we just had to go, oh, there's our cation name, there's our anion name, and that's it. But we saw that there were different numbers of ions present in each one. So if we're going to name potassium fluoride, we have the name potassium fluoride, if we want to write the chemical structure for it, how do you know how many to include? Is this going to be, so potassium is, has a chemical symbol K. Fluorine has a chemical symbol F. But how do you know what this is going to be? Is it going to be KF? Is it going to be KF2? Is it going to be K3F? How do you know what numbers go in the chemical formula? It's a significant challenge. And the answer to that question, the way you figure out what ratio these two ions will combine in, you get it by looking at the periodic table. All right. What you have to do is you have to look at where the ion falls on the periodic table. Then you have to ask yourself this question. What is the nearest noble gas to the ion that you're asking about? Now, first off, you might be just going, well, what is a noble gas? I have no idea what you're talking about, Josh. The noble gases are the last group on the periodic table right here. All right, these are the noble gases. They're called that because these elements here on the last periodic table are insanely stable. They're some of the last elements that we discovered scientifically, and the reason why is they're so stable, they never react. They're non-reactive. They're like just zen. They're blissed out. They don't want to gain electrons. They don't want to lose electrons. They won't engage in reactivity like the rest of the periodic table. And we're going to get into this more later in the semester, but the key to their stability is their electron count. There's something very, very special about the electron count of each noble gas. And again, I'm not going to explain it at this moment. We'll dig into it a little more later in the semester. But every main group element wants to have the same electron count as a noble gas because that is stable. And that desire of every main group element to have the same electron count as its nearest noble gas is the motivation, is the reason why elements become ions in the first place, is they're trying to achieve that noble gas configuration. So for example, if you look at fluoride, sorry, let me clear a little space here. So let's take a look at fluorine. Fluorine, which is right here, has an atomic number of 9, which means that fluorine has 9 protons in its nucleus, and when fluorine is a neutral element, fluorine has 9 electrons. Now, what is fluorine's nearest noble gas? Well, fluorine is closest to neon, and neon has 10 protons and 10 electrons. Now, the proton count for an element is not going to change. But what fluorine is dying to have the stability of neon. The stability of neon's 10 electrons. And what fluorine will do is it will gain 1 electron to become an ion. So watch what happens when fluorine gains 1 electron. It still has 9 protons, but now it has 10 electrons. And now, 2 things. First, it has the same electron count as neon, so it gets that stability that neon enjoys. But notice that the proton and electron count is no longer equal. For fluorine as an element, it has 9 protons, 9 electrons. Your positives and negatives cancel. But now we have 1 more electron than we have protons. So there's 9 positive charges. That only cancels 9 out of the 10 of our negative charges. So fluorine, neutral, becomes fluoride, which has a negative charge. All right, so now fluoride is an ion with a charge of -1, and we determined that by looking at fluorine's position relative to its nearest noble gas. It gained 1 electron to have the same electron count as neon, and now it has a charge of -1. Let's use the same analysis, the same analytical method to determine what charge potassium will develop by looking at its nearest noble gas. All right, so let's look at potassium. Potassium is right here. On the periodic table. Potassium has 19 protons and 19 electrons. Potassium's nearest noble gas, you got to look at the numbers here, is argon. Argon has 18 protons and 18 electrons. Now, potassium, more than anything else, wants to have the same stability as argon, and that stability is rooted in its electron count. So potassium, where fluorine gained an electron to be like its nearest noble gas, potassium is going to lose an electron so that it can go down to an electron count of 18. So now potassium has 19 protons. After losing one, it'll have 18 electrons. Potassium, the atom, is net neutral. There's 19 positives and 19 negatives. But now, as an ion, potassium has lost 1 electron. There are two effects of this. There are 2 consequences of this. 1, potassium is now stable. It has the same electron count as argon, its nearest noble gas. But now, there are 18 electrons to the 19 protons. So potassium has picked up a charge of +1 because the protons, the positive charges, are in excess. Freya, that is a great question. So Freya is wondering, wait a minute, I thought that potassium's nearest noble gas would be krypton, and it's not. Even though they're on the same row, krypton has 36 electrons. Potassium has 19 electrons. So you have to ask yourself, is 19 closer to 36? Or is 19 closer to 18? And it is far easier to lose 1 electron to get down to 18 than to gain, 17 electrons to get up to 36. So you always go for the closest number, not necessarily what period they're on. Freya, let me know if that makes sense. So you're not looking at the period, you're looking at which number is actually closer. All right, so potassium, after losing 1 electron, now has a positive charge, which means awesome. I'm so glad. Which now means that as a cation, potassium has a charge of +1. Once you have determined your charges for your cation and your anion, now you can figure out how many are going to be in each, or what the ratio is going to be in your ionic compound. Because remember, every ionic compound is net neutral, which means that your positives and negatives cancel. So you have to ask yourself, how many +1s you need to cancel one negative? The answer is 1, which means that potassium fluoride has a chemical formula of Kf because you need one positive one to cancel with one negative one. All right, so that is the chemical formula for potassium fluoride. Oops. Let's go ahead and do a few more examples. How about let's write the chemical formula for sodium sulfide. All right, sodium is located right here on the periodic table. Sulfide is over here. And so we've got Na and we've got S. Let's go ahead and start with our anion. Okay, Jessica, great question. So Jessica's asking, so the charge is about closeness to the nearest noble gas, not necessarily the amount of electrons. And the answer is it's actually both. The closeness to your nearest noble gas will determine the number of electrons you need to gain to attain that. So it's actually the same thing. Now, the good news is, so with that last example, I was writing out like the number of protons, the number of electrons, but you won't actually need to be that explicit every time, because you can get there by just counting, by basically just looking at the periodic table. So, for example, you notice that sulfur is here. All right, we want to figure out what our charge is. Its nearest noble gas is argon. Right, sulfur has 16, argon has 18. That's closer than 36. That's closer than 10, right? 18 is the closest. So you have to ask yourself, how many electrons do you need to gain, if you're sulfur, to get 18 electrons, which argon has? And you can just count over with the periodic table. You can go 1, 2. So sulfur, to attain argon's electron configuration, needs to gain 2 electrons, which means it needs to pick up a charge of -2. Sulfide will have a charge of -2. Sorry, I gotta make a little space here. Now, if you look at sodium, sodium's nearest noble gas is going to be neon, right? Sodium has 11, neon has 10. Sodium needs to lose 1 electron to have the same electron configuration as neon, which if you're losing 1 negative charge, that means you will have a charge of +1 left over. So sodium's +1, sulfide's -2. Now we're ready to write our chemical formula. And so you have to ask yourself, how many +1s do you need to balance with a charge of -2? Well, the answer would be 2. If your total positive charge must cancel out your total negative charge, then you need 2 sodiums, 2 sodium cations, to balance 1 sulfur anion. All right, it's about mid-lecture, which means we're switching from coffee to LaCroix. All right, so this is the chemical formula for sodium sulfide. All right, let's do another example. Let's do calcium iodide. All right, calcium is located here. Iodine is right here. And you can see that with iodide has 53 ions. Its nearest noble gas is xenon, which has 54. So iodine needs to gain 1 electron to have the same number of electrons as xenon. So iodide, after gaining that 1 electron, will have a charge of -1. Let's look at calcium. Calcium has 20 electrons. Its nearest noble gas is argon, which has 18. So calcium has too many electrons. It has too many. So it's going to lose 2 negative charges to drop from 20 electrons down to 18. Once it does, loses those 2 negative charges, it will have leftover positive charge of 2. So calcium is +2. Iodide is -1. Now you have to ask yourself, how many negative iodides do we need to bring to balance with this total charge of +2? The answer is you need 2 iodide anions for every calcium cation present in your molecule. All right. So we're going to do one more example before we introduce the next layer. All right, let's do magnesium nitride. Nitrogen is located right here. Magnesium is right here. All right, so we've got to figure out our charge for our cation and our anion. If you look at magnesium, magnesium's nearest noble gas is neon. Magnesium has 12 electrons, neon has 10, so magnesium needs to lose 2. When you lose 2 negative charges, you're left with a charge of +2. Let's look at nitride. Nitride's nearest noble gas, also neon. So nitrogen has 7 electrons, neon has 10. So nitrogen needs to gain 3 electrons to have the same electron count as neon, its nearest noble gas. So after nitrogen gains 3 negative charges, it will have a total charge of -3. Now this is where the rub comes in. Up to this moment in time, our positive charge, either our positive or negative charge has gone into the other evenly. But 2 does not go into -3. How are we going to solve this? There's a quick and dirty trick for determining how to balance your charges to get net neutral, which I'll talk about in just 1 second, because we have a question in the chat. Freya. So, oops. So Freya's wondering how, again, we're determining which noble gas is the nearest noble gas, and it is whatever noble gas has the closest electron count. So, for example, if you look at magnesium, magnesium has 12 electrons. So you have to ask yourself, of all the noble gases, which one has the closest electron count? And the choices we have are 2, 10, 18, 36, 54, 86, and 118. And the one that is closest to magnesium's 12, is neon. Because 10 is 2 numbers away from 12. 18 is 6 spaces away. 2 is 10 spaces away. So neon's the closest. You look at all the possible options and ask which number is closest to this one. And that's how you zero in on your nearest noble gas. Okay, let's see other question in the chat. What would happen if the element is located in the middle? Oh, interesting. Okay. That is a great question. So Alexander, to answer your question, let me finish doing this problem, and then Alexander, I'm going to get to yours. Okay, so let me finish this magnesium nitride thing, and then I'll come back and hit your answer. So we're dealing with this conundrum with magnesium nitride where 2 does not go into 3 evenly. So how are we going to figure out our charges? There's a quick and dirty way to get straight to the correct answer here. You know that magnesium nitride is going to have magnesium in it, and it's going to have nitride in it. What you do is you take your positive charge, make it the subscript for your anion. Then you take your anion's charge and make it the subscript for your cation, and that is your chemical formula. Do this whenever you have 2 charges that do not go into each other evenly, and this will give you the right answer every time. All right. So now, Alexander, what happens if you have an element that is dead in the middle? For example, like carbon or silicon. I'll zero in on carbon. So how do you determine the nearest noble gas for carbon? Carbon has 6 electrons. So if you look, there are 2 candidates for nearest noble gas. One is helium, one is neon. Helium's above with 2 electrons. Neon is below with 10 electrons. And you'll notice that carbon is 4 electrons away from neon, and carbon is 4 electrons away from helium. How do you pick? How do you choose? They're the same distance away. Here's the thing. Carbon has a hard time choosing. Does it go with helium? Does it go with neon? Because it's literally dead center. And because of this, carbon rarely forms ionic compounds. Carbon rarely forms ionic compounds for this reason. It's if an element is closer, like over here in this range, it'll want to gain electrons to become like its nearest noble gas. So it'll be an anion. Anions are over here. If an element is over here, then it wants to, I just realized you may not be able to see my... Oh, wait, yeah, you can see my cursor. Okay. If an element's over here, it's going to lose electrons and become a cation. Carbon is dead center. It doesn't know whether it wants to be a cation or an anion. It just prefers to not choose. Which is why carbon typically forms covalent compounds. Now, you should know that carbon can form ionic compounds. This is an example. My ring is made out of tungsten carbide, in which case it is an anion. So they do exist. There are examples of carbon being an anion or rare cation. It can exist. But they're so rare that I'm not going to test you on them. So you're only going to run into carbon during the covalent portion of this chapter. I will not give you an ambiguous case where you have an element that could lose electrons and be a cation, could gain electrons and be an anion. So you don't have to worry about that. Hopefully that eases your anxiety. All right. All right. Now, so we're one of the things you may have noticed up to this moment in time is all of the examples that I have done have involved, whoa, not what I was trying to do. This is what I was trying to do. All the examples I have done so far have involved elements from the main group. The cations and anions have been selected from the main group of elements, and that's been purposeful. That's been purposeful because the transition metals are a very different breed of ions. These are all cations, but they are not predictable. The main group is nice because they always have the same charges. You don't have to worry about them. The transition metals, however, have a variety of charges. So, for example, sodium. If you turn your attention to sodium, sodium is always +1. If you look at oxide, oxide will always be -2. All right. This is not the case with the transition metals. If you look at chromium, chromium can be +1, +3, or +6. If you look at nickel, nickel could be, oops, that's sodium. If you look at nickel, nickel could be +1 or +2. That's it. Zinc is only +2. Lanthanum is always only +3. Oh, why not? Iron, +1, +2, +3. +5. +8. All right, the transition metals are all over the place, and there's no rhyme or reason. There's some general trends, but there really isn't a rhyme or reason as to what charges these things can have. If that strikes fear into your heart, totally don't worry about it. This is actually good news. This is good news, and let me show you how. When I give you a main group compound, like name, like magnesium chloride, it's up to you to find magnesium on the periodic table, locate its nearest noble gas, and determine its charge. Okay, so magnesium's +2. And then we got to do the business with chlorine. Being right there, chlorine is a -1. Okay, so +2, -1. Okay, magnesium chloride's MgCl2. I cannot give you, I can't write vanadium chloride and ask you to name it, because vanadium is a transition metal. You have no way of knowing what that charge on vanadium is. And here's why it's good news. I can't tell you vanadium chloride. I have to give you the charge of vanadium in parentheses in a Roman numeral. So I can tell you vanadium, I can ask you to name vanadium 5-chloride, because I have explicitly told you the charge in parentheses. So this is V plus 5. Now, you still have to figure out chloride like normal, but you know how to do that, right? Chloride is a -1. So at first, when I was throwing up all those different charges, it may have been bewildering, and you may have been going, oh no, it's so varied, this is going to be hard. Your life actually gets a bit easier because the charges are so varied. I have to explicitly tell you that you're dealing with vanadium 5 chloride, which means that this will be VCl5, because we need 5 -1s to balance with that +5. All right? So with the transition metals, I have to explicitly give you the charges. And we got time for maybe a couple more examples of this. Oh my, okay, here, hang on. I just messed up my whiteboard. There I go. Okay. All's well that ends well. So, how about we do let's write the chemical formula for nickel 2 oxide. Well, oxide is oxygen. Its nearest noble gas is neon. So this will be O with a charge of -2. Now nickel, we don't have to look at the periodic table because we were told that it has a charge of +2. So +2, -2, this will combine in a 1-to-1 ratio. Nickel 2 oxide is NiO. What about, let's get weird. Let's do something like osmium 8 oxide. That's feeling uncreative. The cool thing is, you don't even need to find osmium on the periodic table, though you can, it's right here. But that position won't tell you anything. What will tell you something is what I've told you in parentheses right here. Osmium has a charge of positive 8. Oxide, as we already know, has a charge of negative 2. 2 is going to go into 8 4 times, so this will be OSO4. That is osmium 8 oxide. All right, now, when you're dealing with transition metals, and I give you the name of a compound, it's fairly easy. We could even make the argument easier writing the chemical formula than it is for regular ionic compounds because you're explicitly told your cationic charge. But it's a little more challenging when you have to move from the formula to the name. So for example, name the following. This is where things get a little more challenging because iron is a transition metal, right? When you look at it, iron falls squarely in the middle of the transition metal block, right? The D block. And we can't name any of these iron oxide. If this were lithium, we could call them lithium oxide. We can't name these things iron oxide because if we did, we would name all of them iron oxide. And as you can see, they have different chemical formula. These are 4 different compounds comprised of iron and oxide. So when you are naming an ionic compound with a transition metal, it's not enough just to say iron oxide. You have to figure out the charge and put it in parentheses in Roman numerals after iron. And that is the take-home message here. The charge is part of the name. When you're dealing with transition metals. Now, it is 12:49. We're gonna put a pin in lecture right now. This is where we'll end. On Monday, we'll resume by doing these 4 examples, and then we'll continue looking at nomenclature. But I encourage you to take a shot at this over the weekend. See if you can name it. Get going on exercise 2. And really, each of these are going to be iron something oxide. The real mystery is, can you figure out the charge that goes in this parentheses every single time? And I will give you this hint. It will be different every single time. So take a shot at that. We'll pick it up on Monday and continue with our discussion of nomenclature. Have a great weekend, dudes. I'll catch